All right. So hello, guys, and welcome back to Professor TK the Chemist channel. Learn chemistry with Professor TK the Chemist. If you are ready to learn the next topic in chemistry, say ready. Are you ready? Let's go. Let's get it. So, on this first part, it says in the reaction, HCl plus H2O produces H3O plus Cl. Identify the Brønsted-Lowry acid-base, conjugate acid, conjugate base. Explain why HCl is classified as a strong acid. So anytime we are doing problems like this, what I always tend to do with my students, I have them label it. And when I say label, I'm saying you're going to identify what you're working with like this. Okay, let me show you what I mean by that. All right. So right here, when we know what one thing is, the other one is going to be the exact opposite. Okay, it's going to be the exact opposite. So right here, if I know that HCl is an acid, okay, then guess what? Water is a base. And then I'm going to look for the one that looks like it on the opposite side. Then that one is going to be the conjugate of that other thing. So if HCl is an acid, the Cl is going to be the conjugate base. And because H2O was a base, then H3O plus, that one is going to be the conjugate acid. Okay? It is that simple. It is that simple. So whenever you're doing these problems, you've got to understand that knowing one versus the other will help make these other problems make sense. Okay? Now, why is HCl classified as a strong acid? All right, Munn said HCl is a strong acid because it dissociates completely. It has a high Ka value. Okay, I'm glad you brought up the Ka value because that's also utilized in these titration problems and buffer solutions. Okay, and then you also said that H3O plus is a conjugate acid and chlorine, yes, is a conjugate base. Okay, very good, very good, very good. Here's some other notes that you may want to know because it says identify the Brønsted-Lowry acid and base and then conjugate acid base. So we did that already, right? The Brønsted-Lowry acid is the HCl because it donates a proton. So HCl donates a proton. The base, H2O, accepts a proton. It accepts a proton. So when you look at HCl and compare that to the conjugate base of Cl, it formed when HCl loses a proton, okay? And same thing for the conjugate acid is formed when H2O accepts a proton. So you want to make sure that you guys remember that as well, all right? Make sure you all remember that. All right, let's take a look then at the next example, the one underneath it, okay? Let's look at the next one right here. So we're going to scoot this up, all right? And again, I'm going to take this out because I want to, kind of highlight it and show how we can easily label it, okay? So we are going to label this. And again, you all can participate. You can engage by placing your answers in the chat box. All right, so take a look at this next one. It says acetic acid reacts with water according to the reaction. Identify the conjugate acid-base pair and explain why acetic acid is considered a weak acid. All right, so what we already know here, we already know that acetic acid here, hint, hint, that is an acid. And water, in this case, is a base. Side note, water is what we call amphoteric, okay? Amphoteric. That means it can behave like an acid or a base, okay? It can behave like an acid or a base depending on the situation and the environment. All right, so now if we already know that CH3COOH is the acid, look for its twin without the extra hydrogen. On the other side, that would be considered its conjugate base, okay? It's conjugate base. Then when we look at base for water, we know that the one that looks like it's twin or close to it, that is H3O plus. That would be classified as a conjugate acid. Okay, let's go ahead and move on to number 3. Again, these are warm-up problems, okay? Warming up problems. Warming up problems. Because then what we're going to do is do some calculations, such as what you guys see here in number 4 with the equilibrium reaction, okay? So we're going to do that also coming up. So let's go ahead and get into number 3. All right, so NH3 in this next example, we know that NH3 is a base. Yep, we know that's a base. So if that's a base, then H2O is an acid. And if you guys remember what I said earlier up here, water is considered to be an amphoteric compound, meaning it can go either way, depending on its environment. It could be an acid or a base, okay? It's a universal solvent, all right? Now, if you look at NH3 as the base, then you know that the NH4 is the conjugate acid. It looks similar to it, looks like it's twin. H2O is the acid, so look for the twin on the other side. Therefore, it is a conjugate base. Okay? All right, so let's look at number 4, okay? Number 4, you have, they want you to write the equilibrium constant. They want, basically in number 4's problem, all you're doing is writing out, of course, the conjugate acid base pairs, yes. And what you're going to do, identify the conjugate acid base pairs and write the equilibrium reaction of HF with water. So you got to figure out how to write this out, okay? So for number 4, we're going to determine how to write this out, okay? How do you write this out? So far, you've been given the chemical reactions, but this time, it's a little different because now you've got to provide that, okay? You've got to provide it. All right, so let's take a look at how do you do that, all right? How do you do that? So for number 4, because they told you you have HF with water, put those two together, all right? So you've got HF plus water. And remember, they said that equilibrium is just like this. And now, let's see if you guys can remember from what we did previously. Let's go ahead and identify what we got. We know that HF is an acid. And we know that water is a base. So, what am I going to write on this side to form the conjugate base part? What should I write on this side to make it look like the conjugate base? What should I write? Well, because you are removing the hydrogen for the base, you're going to end up with F, okay? F with a negative, all right? And then over here for water, because water is a base, you need to show on this side here that you have the conjugate acid. That means you need to have an additional hydrogen there. So therefore, you end up with H3O with the plus. Now, based on these questions here, we're now looking at Lewis acids and bases, okay? Lewis acids and bases. So is there a difference? Let's determine that now. Let's go ahead and determine that now. So let me go ahead and scoot this down to the next part of the screen. Lewis acids, bases. Explain why this reaction cannot be described using only the Brønsted-Lowry theory. So for number 5 right here, for number 5, okay, for number 5, when you look at this reaction, matter of fact, let me go ahead and plug it here so you all can see it. Aluminum chloride doesn't look like the same thing on the opposite side. And NH3 doesn't look like the same thing on the opposite side. So what we need to do here is determine what we've got. And like, what are we working with here? Okay. What are we working with? So the Lewis acid in this particular case here is the AlCl3. That is your Lewis acid. Specifically, the aluminum ion that you see there, it accepts electron pairs, okay? It accepts electron pairs. So when you look at AlCl3, right there, that will be considered the Lewis acid. So I'm going to put Lewis acid for this one. Okay, and then obviously you know that NH3 is the Lewis base. Now, Lewis name comes up a lot. Whenever you talk about drawing out those pictures, those Lewis dot diagrams, it is for this reason right here, okay? It is for this reason right here. So that's why that's what I mean about how everything comes full circle, where you see how some of these elements come around. It's because of what you have to learn in previous chapters that come back to help you in future chapters. So again, in this case right here, the Lewis acid is AlCl3 because the aluminum ion, 3+ ion, accepts electron pairs. And then for the NH3, it donates electron pairs. The reason why this cannot be classified as a Lewis Brønsted-Lowry theory is because it doesn't involve proton transfers, okay? It doesn't involve proton transfers. The Lewis theory is more comprehensible because it actually shows how you are able to define acids as electron pair acceptors and bases as electron pair donors, okay? That's the reason. That is the reason. Okay, so you all know lactic acid is responsible for muscle soreness after intense exercise. Yes, guys. How many of y'all have ever been sore from working out? That's a good thing. They always hear athletes say pain is motivational. Pain means improvement. Pain means you're reaching your goals. Well, in this case, when it's dissolved in water, it establishes the equilibrium of of lactic acid and water. So as you can see on the other side, you have CH3H5O3 plus H3O plus. Identify the conjugate acid base pairs and explain why lactic acid produces muscle soreness in terms of acid-base chemistry. So let me hear if you guys can kind of give me the chemistry behind lactic acid. I'm curious. I am curious. So as we can see here, HC3H5O3, that is the acid. We know that water is the base. So find its pair on the other side. That's going to give you what? Right. Hey, Zach. Yep. Conjugate base lost. That's right. It lost the hydrogen because after it was depronated, it is more likely to accept what? Yes. That is correct. So that is your conjugate base. And now look at water. On the opposite side here, you have H3O plus. So that would be your conjugate acid. So y'all, again, these are not hard. You know, I keep saying that because I want you all to understand and see that. Don't make this difficult, okay? Do not. Lactic acid, again, is a weak acid that partially dissociates in water. So the chemistry behind this means that because of the weakness of the lactic acid, usually contributing to the problem, weak acid means it can persist in tissues longer than a strong acid might, okay? So that's the science behind it. That's the chemistry behind it. It can persist in the tissues longer. So a weak acid lingers around longer than a strong acid might, okay? All right. Number seven. Again, we should be getting through these quick. Why? Because, whoops. We should be getting through these quick because by now you should see how easy they are, how simple they are to do. If you look at this next one, you have sodium bicarbonate. It's often used as an antacid. Okay, when it reaches with stomach acid, HCl, the following reaction occurs. Okay, this is like a neutralization reaction, by the way. Hint, hint. So if your stomach is ever sour, And because of all the acid buildup, you know, from eating spicy food or whatever the case may be, you can actually take a tablespoon of baking soda and then put that in water, of course, because you don't want to just swallow baking soda whole. And when you put that in water and then drink it, it'll actually neutralize that acidic buildup. Okay? Hint, hint. We should be able to knock this out the box. NaHCO3, that is the base. Okay, if you didn't know that, well, now you do. This is your base right here. Let me scoot this down. Hold on, y'all. This is your base. If NaHCO3 is a base, then obviously HCl is the acid. Look for the twin on the other side. So now I'm going to pause right here. I'm going to see if you all can tell me the answer to this before I continue on. Identify the Brønsted-Lowry acid and base in this reaction. So in this case here, your Brønsted-Lowry acid is the HCl and your base is the HCO3+. Now, when that bicarbonate accepts a proton from HCl, it forms carbonic acid, which immediately decomposes into water and carbon dioxide. Okay, so that decomposes into that. All right. So again, in this particular case here, this is what you've got. And also, we could put this as a side note. HCO3 with the negative charge would be the Brønsted base. So if I ask you to write it out, okay, you would say NaHCO3, okay, that is the Brønsted-Lowry base, okay? When you write it out like this, the HCO3 in this particular way right here, okay? When you write it out like that, that would be classified as your conjugate acid, okay? That would be classified as your conjugate acid. And again, we know that HCl is our acid, but remember, because of what's happened, you have to write that Cl minus, that would be the conjugate base, okay? If you were to go a step further, if you were to take this a step further. All right, so for number 11, and this is not even a calculation problem. This is just basically writing out the equilibrium reaction when aspirin dissolves in water. All right, so right there, they're giving you the formula for acetic acid is C9H8O4. They told you it dissolved in water at equilibrium. So what are we going to write on the opposite side? What are we going to write on the opposite side? That's the question I want to know. What should we write on the opposite side? We practiced several examples already, guys. So you all should be writing in the comment chat box what we should write. Remember, we're going to have one less hydrogen. For the C9H8O4, one less hydrogen. And for H2O, one more hydrogen or one additional hydrogen. So for the other side, you're going to put C9H7O4 plus H3O plus. All right. So again, what you've got here, you've got your acid right there, the C9H8O4. And then the conjugate base is right there. That's your conjugate base. And if acid is C9H8O4, then your base is H2O. And so the one that looks like it on the opposite side, let me go ahead and make this smaller so I can write this a little bit above, okay? Then this, of course, is your conjugate acid, okay, right here. Okay, that's it. You need to remove, that's right, you need to remove the hydrogen on the other side to get to H7 instead of H9. Okay. All right. So, well, we only got to 12,000 and it's 1 p.m. now, my time. So, guys, I will see you all on Monday. So, if you all are wanting to learn this information, come on back through on Monday. You guys have an amazing weekend. See you on Monday.